We are now in section 5 of part 4b, where we are now going to talk about stability criterion, and this is page 32. When we say a system is stable, it means that the system does not blow up when we give him a bounded input. So the stability criteria we are talking about specifically is something called BIBO. When the input is bounded, the output is bounded. And we have seen in the first part of this course that this only happens when the impulse response, h of t, is absolutely summable. Or I should say, does not go into infinity. Maybe let's derive this one more time. The output is equals to the convolution of the input and the impulse response. The absolute value of this is of course the absolute value of this, and now we are going to manipulate. We move the absolute into the inside, and therefore this expression is greater than the previous expression. We then again introduce the operator on each of them, and therefore this is definitely greater than the previous expression. We then say that xt is bounded by b. So we can move, that means we say that bx is larger than any of the xt. So we're going to move xt out as bx. And therefore the only term that, and bx is not infinity, the only term that can affect output is the integration of the impulse response. And if the this integration, it exists and it doesn't go to infinity, therefore the output will not go into infinity. That's what it means. So to make the long story short, as long as the impulse response is absolutely integrable, then the system is called BIBO, which is a sufficient condition for BIBO stability. So what gives? We already know that the impulse response tell us that the system is BIBO. Does the Laplace transform tell us the same thing? In fact, the Laplace transform tell us whether the system is stable or not even more quickly. Why so? Well, let's begin with the Laplace transform of the impulse response. Gives you h of s. H of s relate y of s to x of s, and the equation on the numerator is some polynomials of s times constant coefficient b, and here in the denominator is a times some polynomial equation again. Now, when we have this, remember we will factorize this, and the factorization is dependent only on the denominator, because what we will do is that this denominator will generate all these partial fractions, and then of course k is dependent on the numerator as well as the denominator. Now, but it is the denominator that is important. This s, these p's that makes the s goes into infinity are called the poles. The positions of the pole, for example, 1 over s minus p, means that at s equals to p, the whole system blows up. So the position p is the pole position. The quick answer to the question is, if the pole lies on the left hand side of the j omega axis, then the system is stable. Let us find out why. Remember that we have already reduced our partial fraction into this, and each of these will give us an exponential. Whether it is decaying or growing depends on p. So k1 over s minus p1 becomes k1 ep1t in the time domain. Now remember, if we have p poles, then we'll have all these p terms. Let's assume that we are doing non-repeating poles now. Now, the impulse response is sum of all these exponentials. The question, of course, is this the sum going to blow up? Well, first is a finite sum. Second is we now check each individual one of them. Now, how do we check? Well, remember that we are interested in finding whether this sum is absolutely integrable or not. This impulse response. Let's assume first it's a causal exponential from 0 to infinity, and let's begin with e minus at. Now, the integral of this is, of course, 1 over minus a e minus at, starting from 0 to infinity. You can reduce it to 1 over a if a is greater than 0. That means minus a positive number. The exponential will be decaying. Now, to get minus at, then the poles must be on the left hand side, must be less than 0. So these guys must be minus 1, minus 2, minus some real numbers or whatever, but they must lie on the left hand side. So if each one of them is summable, then the sum of a finite sum is summable. So that's what we are trying to prove here. Okay, and of course, once we have observed this, then we now say that as long as the pole lies on the left hand side, then the system is stable. Right, let's have a graphical look at where the pole positions are. So in this example, the pole is along the real line. The pole is at the origin. The pole is along the real line, but on the right hand side. How does the time response of the exponential looks like? On the left hand side, the exponential is decaying. On the origin, then is e to the power 0. It will be a constant value 1 for all time. So if you have an impulse response that sits in the origin or along that line, you are going to integrate to infinity. Okay, and this is marginally stable, or actually you can think of it as unstable. But on the right hand side, it is growing very, very fast. So this is definitely unstable. So a pole sitting on the right hand side of the origin of the j omega axis is definitely unstable. What about a complex pole? Well, when we have this kind of expression here, this is a complex pole. Notice that the pole position is a complex conjugate of each other. The numerator is also complex conjugate of each other, so that together they would produce a real response. Now, poles sitting on the left hand side, it will oscillate and it will decay. So this pole and this pole together form this. Poles on the origin simply decays. Poles on the right hand side of the j omega axis grows. If we have complex conjugate poles, it will oscillate and it will grow. So again, it shows that when the poles are on the right hand side, it is unstable system that we have. Poles on the left hand side, it is stable. Okay, with that, we're done with Laplace transform. Thank you.